Before we start to take a look at characteristics at each layer of the OSI model, we need to define some terminology. Specifically, how do we refer to data? What name do we give data at different layers of the OSI stack? These names are referred to as PDUs, Protocol Data Units. Down at the physical layer, data can be represented as bits, ones or zeros. On a copper cable, a binary 1 might be the presence of voltage. A binary 0 might be the absence of voltage. Up at the data link layer, a PDU is a frame. That's what we normally say at layer 2. However, and there is some debate about this, but Cisco documentation tells us that we can use the term packets to somewhat generically refer to data at layers 2 and 3 and 4. Some people get a bit upset about this. Some people, the purists, say that packets should only refer to a network layer, a layer 3 protocol data unit. However, Cisco says we can generically use the term packets regardless of whether we're talking about layer 2, layer 3, or layer 4. Generally, we will not. Generally, we tend to use the term frame at layer 2 for a protocol data unit, but if you see it in some of the literature, it is technically okay according to Cisco to use the term packets, even down at layer 2. At layer 3, that's where we normally do use the term packets. An alternate term that we could use at layer 3 to refer to data is datagrams. And finally, at layer 4, the transport layer, we could again use the generic term packets, or more specifically, we'll use the term segments. This means that normally we're going to be saying segments for layer 4, packets for layer 3, frames for layer 2, and bits for layer 1. And as a memory aid for you, you can remember this acrostic going from the top down. Some people fear birthdays. Some people fear birthdays. The S in some reminding us of the S in segment, the P in people reminding us of the P in packets, and so on. That's going top down. Another acrostic, if you prefer to go from the bottom up, is bacon frying produces salivation. That gives you quite a visual, doesn't it? Bacon frying produces salivation. A couple of memory aids for you to remember the protocol data units at different layers of the OSI stack. Now, let's jump in to the first layer, layer 1, the physical layer, and think about some of the responsibilities of the physical layer. One responsibility of the physical layer is we determine how bits, ones and zeros, are going to be represented on the medium. And again, if we had copper cabling like unshielded twisted pair, the presence of voltage might be a binary 1, the absence of voltage might be a binary 0. This approach is referred to as current state modulation. You notice I have some individual vertical lines representing each time slot where each bit is going to be represented, and we can either be at 0 volts, we could be at positive 5 volts, or we could be at negative 5 volts. Right now, in this first time slot, we have 0 voltage, and 0 voltage could be interpreted as a binary 0. It's going to be a binary 0. Again, this is called current state modulation. If we're currently at 0 volts, and currently we have a binary 0, we see in the next time slot we have 0 volts. That results in another binary 0. In the next time slot, another 0 voltage potential, another binary 0. But look at this. In the next time slot, we have a binary 1 because we have positive 5 volts. That gives us a binary 1. The next couple of time slots give us binary 0, 0 volts, 0 volts. However, notice what happens in the next time slot. It's the presence of voltage, but it's not positive 5 volts, it's negative 5 volts. But it is voltage, so it's interpreted as a binary 1. And finally, we have another 0 volt interval, so that's going to be a binary 0. Let's think about, though, why we alternated the polarity of our voltages. What I have diagrammed here is something called AMI, alternate mark inversion. With alternate mark inversion, the goal is to have an average of 0 volts on the wire. This is a desirable electrical characteristic, to have an average of 0 volts on the wire. So what we do is send positive 5 volts one time and negative 5 volts the next time. And then the next time it's going to go back to positive and then negative. That's why it's called alternate mark inversion. We're alternating the polarity every time we represent a binary 1 with the presence of voltage. To give you a metaphor, let's imagine that I take one of my hands and I stick it in a bucket of ice cold, freezing water. And I take my other hand and I put it in a pan of boiling hot water. On average, I'm going to be comfortable. Okay, that does not work with humans, but that is the way it works with alternate mark inversion. On average, we have 0 volts on the wire. That's current state modulation. Let's contrast this with state transition modulation. With state transition modulation, it's not the presence or the absence of voltage that determines whether we're representing a binary 1 or a binary 0. It's whether or not the voltage has changed. Has it transitioned from its previous state, from its previous timing interval? Notice in this first time slot we have 0 volts. And we'll assume that the previous time slot was also 0 volts. That would have given us no transition, so we have a binary 0. The next time slot also has 0 volts, but it's not just the fact that it's 0 volts, it did not transition from the previous time slot. Therefore, no transition means a binary 0. Again, the third time slot, no transition from the previous time slot, that gives us a binary 0. Now we do have a transition. We're now at positive 5 volts. But it's not just the fact that we have voltage, it's the fact that there is a transition from the previous state. We transition from 0 volts to 5 volts. That transition means we have a binary 1. In the next time slot, we have 0 volts, but check this out. This is very different than current state modulation because we have transitioned from our previous state of positive 5 volts to 0 volts. Even though we're at 0 volts, that transition still gives us a binary 1. No transition in the next time slot. That's going to be a binary 0. We transition again in the next time slot. We're at negative 5 volts. That transition, though, from the previous time slot means that we have a binary 1. Same thing with the next time slot. We've transitioned from negative 5 volts to 0 volts. Even though we're at 0 volts, it's a transition. And with state transition modulation, that means we have a binary 1. Wiring standards are also determined by the physical layer. How do we wire up, for example, an RJ45 connector? There's a standard, the TIA EF568B standard, that says we're going to be using certain colored wires on certain pins of an RJ45 connector. And we're only going to be using pins 1, 2, 3, and 6 in that 8-wire connector for Ethernet communication. That's an example of a standard that's defined at the physical layer. Physical topologies, those are defined at the physical layer. Here we're talking about how things are physically interconnected. We've got PCs coming back to a wiring closet switch. That would be a star topology. An older Ethernet network might be connected in a bus topology, for example, 10 base 2 or 10 base 5. An FDDI network might be connected in a ring topology. So physical topologies, ring, star, bus, those are examples of things defined at the physical layer. Something else the physical layer is responsible for is synchronizing bits. We've got a couple of devices on a wire, for example. They're trying to communicate between themselves. They're representing bits somehow, the presence or the absence of voltage perhaps. But how do they agree on when one bit stops and another bit starts? There are a couple of basic approaches to synchronization. The first is asynchronous synchronization. With asynchronous synchronization, the sender sends a start bit to say it is about to start transmitting bits. When the receiver sees that start bit, it starts an internal clock, and it expects to see a bit at regular clocking intervals. When the sender is done, it sends a stop bit to indicate that it is done transmitting for the moment. Another approach is synchronous communication. With synchronous communication, both the sender and the receiver determine when one bit stops and another bit starts based on their own internal clock. However, to make sure that the clocks match up, they frequently reference an external clock out on the network. For example, a clock coming from a service provider. This reminds me of the saying that a man with one watch always knows what time it is. A man with two watches is never quite sure. We want to make sure that we have one watch. We have one reference point, maybe the service provider's clock, that both parties can use to set their own internal reference clocks. Another responsibility at the physical layer is bandwidth usage. We've got some sort of a medium, maybe wireless, maybe a coaxial cable, maybe fiber optic cabling, but there are different frequency ranges that can be transmitted over our medium. One approach to bandwidth usage is broadband. Broadband is going to take the medium, like a coaxial cable or a fiber optic cable, and have different ranges of frequencies, and we can send different transmissions on different frequency bands. This is a lot like cable TV, where you tune in your television to a different channel. Well, that channel is represented by a range of frequencies. You can go to another channel, a different communication flow, if you will, and that's represented by a different range of frequencies. However, instead of using broadband, another approach is to use baseband. With baseband communication, all of the frequencies on the medium are used to carry a single conversation, which leads us into our final bullet on screen, and that is the multiplexing strategy. How do we send more than one conversation on a single medium? There are different approaches. One approach is called TDM, time division multiplexing. With time division multiplexing, we have different channels that are given different time slots. Let's take, for example, a T1 circuit that has 24 channels. We could say that channel 1 gets to transmit for a period of time, followed by a reserved period of time for channel 2, and then channel 3, and so on and so on. To paraphrase Whitney Houston, with time division multiplexing, each channel has one moment in time. However, what if we have all of these channels, but at the moment, some channels really don't need their moment in time. They don't have anything to transmit at the moment, while other channels are just bursting to transmit more and more. They have a high bandwidth demand at the moment. There is a way to reallocate the bandwidth available on a medium. It's called statistical time division multiplexing. With statistical time division multiplexing, these time slots are dynamically assigned to the different channels based on the current need of those channels. If a channel doesn't need the bandwidth right then, it can be used by another channel that does need the bandwidth. And one other example is frequency division multiplexing. We've already talked about this a bit. With frequency division multiplexing, we give different communications channels different ranges of frequencies, much like your cable TV. And also, that's what's used by cable modems. There's a range of frequencies used to download on your cable modem. There's another range of frequencies that's used to upload using your cable modem. Let's now sum up some of the different things that the physical layer is responsible for. It is responsible for connectors, the standards of how connectors are physically constructed. The physical layer is responsible for wiring. How are things physically wired together? What kind of wiring is being used? And to give you an example of a device that lives at the physical layer, consider the older Ethernet hub. An Ethernet hub, sometimes referred to as a bit splitter because it literally takes bits in on one port and regenerates those bits out of the other ports. It doesn't make intelligent forwarding decisions. It just replicates and then sends out bits out of all the other ports to make sure that the intended recipient gets the data. Unfortunately, the non-intended recipients also receive the data. A hub is not something we want to be using nowadays in the network. However, when you think of a physical layer device, the first thing that comes to my mind is